You got it? Okay, thanks. I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this morning. Thank you for the snow being delayed enough so we can have class today. I just pray to be with us, help us to enjoy what we're doing, and I just pray you give these students just the courage to persevere in the face of difficulty like this class. In your name I pray, Lord Jesus. Amen. I know Calculus 2, and you guys come from a variety of backgrounds. How many people in here had Engineering 131 as their calculus? I know one of you at least. Anybody else? Oh, maybe it's just a later section. Okay. How many people have just AP calculus as a background? So about half of you. How many had 131 here? How many with Sprano? Okay. How many with Dan Joseph? Okay, so I would, if I had to guess, I would say those of you who are coming from AP are at a slight disadvantage. More than anything else, possibly just because you're a little bit rusty, right? Maybe you haven't done calculus in a year or two, but you'll get it back again. So first of all, I wanted to address the unfortunate events of yesterday, and just to clarify, if I wanted the derivative to differentiate inverse cosine of x, right? What would I do? It's not that complicated. I set y equals to cosine inverse of x, all right? And then I say, okay, well, cosine of y is equal to x. Then what do? Differentiate implicitly. This gives me minus sine of y dy dx is equal to 1. And then, of course, I have dy dx is equal to minus 1 over sine of y. But this can be rewritten as 1 over the square root of 1 minus x squared, since cosine squared y plus sine squared y is equal to 1 implies that, let's see here, cosine y is x squared plus sine squared y is equal to 1, or sine y is equal to plus or minus the square root of 1 minus x squared. And then the thing I was getting all wrapped around somehow yesterday, I don't even know how I did it. Let's not even worry about how I did it. So we choose the plus, since the ultimate formula, the result must be negative. Right? I have minus 1 over a square root of stuff. That's negative, as it should be, because as we've talked about, cosine's decreasing. So the inverse cosine must also be decreasing on the domain of its definition. And that's it. I don't know what I did yesterday, but it wasn't necessary. The other thing I was a little bit leery of was explaining to you why, we define secant inverse of x as being what? Our definition was what? That was what? Cosine inverse of 1 over x, right? And I was like, and it follows from that, the definition. But you know what? I'm not going to burn class time on this. Let me just say for you, I'll post a little video about why secant of secant inverse of x is in fact equal to x. I guess I can take 30 seconds of class time to do it, though, can't I? So what is secant of secant inverse of x? So we define secant inverse of x as what? But what is secant? 1 over, yeah. So this is 1 over cosine of cosine inverse of 1 over x, which is what? Which is, right. So this definition, it seemed mysterious to me yesterday, but if I just had the courage to try to calculate for like a minute, we would have understood that it's really just the regular definition in disguise. But that was useful to us because it allowed us to differentiate with the chain rule to discover the derivative of inverse secant yesterday. But that's all the mystery that's there. I still will post a little video. There's that claim on page, I think, 384, and that would take me about 5 or 10 minutes to work through in here, and I want to get to integration by parts today, so I'm not going to do that. So let's get back to the hyperbolics. So guys, the format today, I'm going to finish the lecture, and then at the end I'll take your questions, okay? So let me get through it. We don't have too much more to do before we get to integration by parts. Anyway, so hyperbolics, as we talked about, cosh of x, 1/2 e to the x plus e to the minus x, sinh of x, 1/2 e to the x minus e to the minus x. A question? No? What's the domain of cosh and sinh? Kind of boring. There's no restriction, right? All x. What do the graphs of these things look like? Turns out cosh looks like this, and sinh looks like this, basically. So like the range of cosh x is 1 to infinity, 1 included. Which cosh of what gives you 1? Yeah, cosh of 0 is 1. What else? What other? So that's the basic thing. They're graphs. The other thing important, obviously, you need to know this, is the derivative with respect to x of cosh x is what? It's sinh x. And the derivative with respect to x of sinh x is cosh x. Now, we talked a little bit about some of the identities which are known for cosh and sinh. Let me remind you those. I guess the fundamental one is that e to the x is cosh x plus sinh x. I used that as kind of, that came from my motivational comment about where cosh and sinh are coming from. Remember, they're respectively the even and odd parts of the exponential function, right? And so we also have this. We have cosh squared x minus sinh squared x is equal to 1. That's a fundamental identity. Now, let me add some new wrinkles here. We can also talk about hyperbolic tangent, hyperbolic cotangent, hyperbolic secant, hyperbolic cosecant, and guess how they're going to be defined? Secant of x, hyperbolic secant of x, hyperbolic cosecant of x, hyperbolic tangent of x. How are these going to be defined? Hyperbolic cof of x. See if I can find a better marker. I'll do the first one. So hyperbolic secant is 1 over cosh of x, just like secant's 1 over cosine. Hyperbolic cosecant is 1 over sinh of x. Right? Hyperbolic tangent is what? Yeah, sinh over cosh. And hyperbolic cotangent is cosh over sinh. With these definitions, right, these are definitions, you can derive other identities, right? From this cosh squared minus sinh squared, what do we get? We also, if we divide this by cos squared, what do we get? Yeah. Yeah, hyperbolic secant squared x, yeah. And if we divide this by sinh squared, it gives us a hyperbolic cotangent squared minus 1 is equal to hyperbolic cosecant squared of x. Yesterday I told you about the identities for trigonometric functions, right? There are also identities for hyperbolic functions, much the same. We derived one of those last time, right? What did we derive? What did I do? I mean, in the same way we can derive identities from cosine squared plus sine squared, right? We can get the one involving tangent and secant and the one involving cotangent and cosecant. Last time we also showed what? We showed, if I remember right, we showed what? 2 times hyperbolic cosine x times hyperbolic sine x was what? Yes, cinch 2x. Of course, there are more identities which are known. So let's see here. If I look at, for example, cos squared of x, what would that be? We square that, right? And what's that give us? 1/4 e to the 2x plus 1 plus 1, right? Plus e. Okay. We can simplify that, right? The exponentials. So I've got like 1/2 of 1/2 e to the 2x plus e to the minus 2x plus what? Plus 1, right? See, the 1 plus 1 gives me 2. 2 over 4 is just a half, right? So that's why I put the 1 there rather than a 2 now, because I have a half out front. But this, of course, is what? This is nothing more than 1/2 of hyperbolic cosine of 2x plus 1. So the double angle formula for hyperbolic cosine kind of goes the same way as cosine, right? So I showed section 2, the imaginary exponential stuff, yesterday. And I probably should take a couple minutes to show you guys today to keep you on the same page. This is a good time to do it. It doesn't have much to do with your homework, I will admit that. But it will have a lot to do with your homework next week. So let me just, a little discussion. I'll try to keep it brief. Imaginary exponentials. These are a useful tool to derive trig identities. So I'm taking a break from the hyperbolic section just for a second here because it really fits nicely with this example we just did. Basically, the story is this. If we let I be the imaginary number, so like I squared is equal to minus 1, then Euler's identity states the following. It states e to the I theta is cosine theta plus I sine theta. Now this identity really lies at the heart of what are called phasors in electrical engineering. So this is important math for you guys, although you guys use a J if you're one of those folks. I think it's worth talking about now, if nothing else for that reason. But the mathematics of it alone is very interesting. Now, if you accept this formula, I mean, you can question where the formula comes from. My answer to you would be take more courses. I'll show you there. It's just you have to accept it on faith for now here. But let me show you what it does for us. What is e to the minus I theta? Well, let me do it right here. If you believe what I wrote in red, what you should believe what I'm about to write in black. Cosine is even, right? Sine is odd, so if I replace theta with minus theta, I should get what? Cosine theta plus, well, minus I sine theta. That comes because cosine of minus theta is cosine theta, and sine of minus theta is minus sine of theta. So, for example, these two formulas then, what do we get if we multiply e to the I theta times e to the minus I theta? I mean, there's two different ways you could look at this, right? The one is in terms of these Euler identities I just wrote for you. If you'll allow me this manga-style calculation, which is my stupid way of saying I'm writing this way. So this is also equal to e to the what? I theta minus I theta, right? E to the 0, if there's any justice, that's how it works. In fact, it is. That would be 1, right? Just from laws of algebra for exponential functions. But on this side, what do you get when you multiply that out? Minus I squared sine theta, right? Sine squared theta. You notice that the plus I sine cosine and the minus I sine cosine cancel, right? See that the terms of the imaginary number I cancel out, and we're just left with cosine squared minus I squared. Hey, but what is minus I squared? Is that true? Indeed it is. Now let me show you the analog of, I'm almost there. So if that was the only thing we could do, it wouldn't be that interesting. What happens if we add e to the I theta plus e to the minus I theta? What happens if we subtract e to the I theta, e to the minus I theta from e to the I theta? So what I want you to do is, let me put a box around these and call it Pac-Man. So from Pac-Man, if you add the top and the bottom of Pac-Man, and if you subtract the top and the bottom of Pac-Man, what do you get? What happens when you add them? I sine thetas cancel, right? Right? What do we get here? The cosines cancel, right? Yeah, 2i sine theta. So, hey, that's amazing because now we get formulas for the real functions, sine and cosine, in terms of these imaginary exponentials. So in other words, what this does is it gives me a way of calculating things about sine and cosine in terms of imaginary exponentials. And imaginary exponentials, I know it sounds kind of scary, but it's actually very simple. They just obey the usual laws of exponents. So what I'm about to tell you is you can use the usual laws of exponents to derive trig identities. You don't seem too excited. That's okay. I'll allow it. It's 8:15. So, for example, and then I'll get back to the hyperbolic wonderland we were in. I can calculate the identity for cosine squared theta. This is what? This is 1/2 e to the I theta plus e to the minus I theta, and we square that thing. How did we derive the identity for cosine squared theta last time? We used the adding angle identity, right? We put theta plus theta. It gave us cosine cosine theta minus sine theta. And then we used the Pythagorean identity, and then we solved for cosine squared theta yesterday. So we're taking a radically different approach to that problem now. This gives us what? 1/4. It's the same calculation as that, but now with I. This technique is stupidly general. You can remember all your favorite trig identities using imaginary exponentials. All right. This is just a start. I'll come back to this another day. This is probably not in your book in this way. Some people think you shouldn't show calculus students the Euler identities because it's just formal nonsense. You don't really understand it. Well, most things we do in here are formal nonsense to you. How many of you have constructed real numbers? I mean, no one has constructed real numbers at this point in their education. It's absurd, right? So everything you're working with has a certain degree of formality. You're accepting their existence. You haven't constructed them or something. You can say, well, real numbers are corresponding to the, some line or something geometric. Well, that's nice, but that's not much better than me giving you these formulas and telling you that they're reasonable. I shut up. All right, so back to the world of hyperbolics. I will post some links and stuff in Blackboard. I've had trouble downloading stuff from my website. I don't know what's going on. I don't know if it's like the recent browser. I don't know if my server is doing something funny, but like today I tried to click on some old files I have posted for like Calculus 1, and I can't get anything to load. I don't know what's going on. If you have trouble, getting some resource from my website, you can send me an email, and I'll try to address it. What I'm going to do though, in the meantime, as I'm working on my website problem, is to just post, I'll try to post some of my notes and things in Blackboard, so they're just there, at least the big things like the course, the Calculus 1 PDF and some of those things. And I'll also try to give you a link to point out where in my notes I talk about these things, because I don't think it's in the textbook. All right. So back to the world of hyperbolics. What do we know? The box on 7.8.3, we're also told, so we also have these following identities, like cosh of t plus s is equal to cosh t cosh s plus cosh, plus cinch. And cinch, I know I'm tired of writing these. I'm gonna stop writing this in a second here. Let me get this out of my system, then I'll just tell you. There are similar identities for cosh and cinch as there are for sine and cosine, right? Now, somebody asked here, I guess I'll just stop. Are there any questions about imaginary exponentials before I go on? Okay, this is not your last chance. You can ask about them. I would say tomorrow, but it seems rather unlikely. I would be shocked if classes aren't canceled by 5. All right. tell you what, though. Yeah. Yes, it's wrong. The reason there are 3 T's, I guess I could say women. And I mean, and of course I'm talking about, oh, that's not good either. Fallen man. We're all, we're not perfect. And it really goes back to Eve, right? So, no? Too much? Sorry. Adam was there too. Fine. I hear you. Okay, where are we? So, as much as okay, fine. One other thing. What's the connection between cosh and cinch and sine and cosine then? Check this out. Cosh of I theta would be what? If I put I theta in for x, what do you get? What is and what is that? Yeah, cosine theta. So you see cosh and cinch and sine and cosine are really just 2 sides of the same coin. There's something called the complex exponential function where all of these things get lumped together in one big grand glorious function. But the context to really understand that's complex analysis, which we have a course here. It's Math 331. Of course, you should do other things like take Calculus 3 and such before you do that. But if you understand these imaginary exponentials, though, half the stuff I told you need to memorize last class, you don't need to memorize. You can derive without too much trouble, including the adding angles identities. More on that some other day. So, inverse and other hyperbolic functions I'll try to be brief. So first of all, what happens if we differentiate something like hyperbolic tangent of x? How's that work? What do we got to do? Mm-hmm. Right. So it's not something we really need to memorize. We could derive it, right? I mean, so what do we have? I had quotient rule, right? So I got cosh x times cosh x minus cinch times cinch divided by cosh squared x, right? Ah, man, if only this simplified. Wait a minute. What was our identity? This one, right? Cosh squared minus cinch squared is 1. So this is really just 1 over cosh squared x, which is what? Yeah, hyperbolic secant squared x. So the derivative with respect to x of hyperbolic tangent of x is, in fact, equal to hyperbolic secant squared x. I guess we can do another one. What's the derivative with respect to x of hyperbolic cosecant of x? So you can either use the quotient rule, right, or you could use a chain rule on the reciprocal function. I'll use the chain rule on the reciprocal function. In other words, I'm going like, okay, so this is minus 1 over cinch squared x times the derivative of cinch x, which is what? Cosh x, right? So what do I got? I've got minus cosh x over sinh x times 1 over sinh x, which is what? It's minus cos. Yeah, hyperbolic cotangent times hyperbolic secant times minus 1. Yeah. All right. I leave the other ones to your imagination, but they're in the book, right? It's not surprising. It's almost the same, but beware the minus signs might differ by a little bit here and there. Okay. What else might we care to know about? I'll just focus on the essential inverse hyperbolics in here. There are 3 of them, right? So we'll consider the hyperbolic inverse cosine, the hyperbolic inverse sine, and the inverse, of course, of hyperbolic tangent. I'll just talk about those 3. That should be enough. If we understand those, we should be good to go for now. Now, inverse hyperbolic sine, there's no real issue there in terms of what I mean by that, because hyperbolic sine is 1-to-1 everywhere. It's always increasing. It passes the horizontal line test without any kind of qualification, right? But inverse hyperbolic cosine, that's got to mean something, some kind of special convention, right? Because this fails the horizontal line test. So what the inverse hyperbolic cosine is actually the inverse for the positive part of the hyperbolic cosine. So in particular, cosh of cosh inverse of x is only going to equal to x again for x an element of 0 to infinity. All right, so so let's consider then. We want to calculate the derivatives of these guys. All right. So I'll do 2 of them. Which one do you want me to do? I'll do hyperbolic inverse tangent and one other. You pick it. Sine? Is that the one I assigned you in homework? No, I don't remember. I may not have done it. Sometimes I assign these in homework, but so to calculate the derivative with respect to x of sinh inverse of x, what do we do? 1, 2, 3. This will be our 4th time doing this technique in here. I did it once at the start of today. We're doing that again. Y equals to inverse hyperbolic sine of x. So sinh of y is equal to x. We do then what? Yep. Hyperbolic cosine. Derivative of x is 1. Yep. So I'm going to work sideways as to not get behind the projector. So this is dy dx is 1 over hyperbolic cosine of y. Let me just write off over on the side here. We've got cosh squared y minus sinh squared y is equal to 1, right? In other words, cosh squared y is 1 plus x squared, right? Because sinh y is what? Sinh y is equal to x, right? So I get hyperbolic cosine squared y is 1 plus x squared, which means hyperbolic cosine of y is the square root of 1 plus x squared. Now you might worry that I have to put plus or minus there, but I don't, because we're talking about hyperbolic cosine, which is non-negative. So yeah, the algebra allows for plus or minus, but the definition of hyperbolic cosine does not. So that minus solution in the algebra is extraneous. Okay, so there you go. 1 over the square root of 1 plus x squared. Not too shabby. All right, so here we go. d dx of inverse hyperbolic sine of x is equal to 1 over the square root of 1 plus x squared. What? Any questions about that? I'll just. Okay. So finally, what's d dx of, let's see here, inverse hyperbolic tangent of x? So there's my question. So what do? Same song and dance. Let y equal to inverse hyperbolic tangent of x. What's my next step? Right, you're one step ahead of me. Take the hyperbolic tangent of both sides. We get hyperbolic tangent of y equals to x. Yeah, now differentiate both sides implicitly. And fortunately, we know that the derivative of hyperbolic tangent is hyperbolic secant squared. So I get hyperbolic secant squared y dy dx, right, chain rule, because I'm differentiating a function of y with respect to x. And that's equal to 1. So that gives me dy dx is equal to 1 over hyperbolic secant squared y. Now I don't like, I want to convert it back to what? To hyperbolic tangents. How do you trade hyperbolic secants for hyperbolic tangents? It's up here, right? So this identity says that 1 minus hyperbolic tangent squared, replace x with y, is equal to hyperbolic secant squared of y. But of course, this is exactly 1 minus x squared in view of how y and x are related here. And there you have it. 1 over 1 minus x squared. So therefore, the derivative with respect to x of inverse hyperbolic tangent of x is 1 over 1 minus x squared. All right. And of course, we can do integrations corresponding to these newfound friends. The only other thing that I'd like to talk about, but I'm going to not do it at the moment, is there's some really interesting identities that connect inverse hyperbolic functions and natural logs in some kind of surprising ways. If you look, theorem 7.9.2, we're told 3 identities, which are, I think, a little bit surprising. For example, inverse hyperbolic sine of x is actually equal to the natural log of x plus the square root of x squared plus 1. The derivation of such identities is actually not that hard, but I probably don't have time to do it today. So here's the first one. There's, if you look at theorem 7.9.2, there's 2 more. There's also one for, well, here, I'll do the inverse hyperbolic. There's one for hyperbolic inverse cosine, but I'll do the tanh inverse one, too, because it's kind of interesting. The inverse hyperbolic tanh is 1/2 the natural log of 1 plus x over 1 minus x. Now, that's for minus 1 less than x less than 1. I think that one's probably the most interesting one, given what we just talked about. That suggests that the domain for inverse hyperbolic tanh is what? I mean, if that formula is how things usually go, the formula will be as greedy as it can be. You notice I have not talked about what the graph of tangent looks like yet, have I? What does it look like? On the basis of that formula, I expect it has horizontal asymptotes at plus or minus 1. So tangent of x is what? It's Cinch over Cosh, right? But you notice the halves cancel, and you get what? You get e to the x minus e to the minus x over e to the x plus e to the minus x. How can you simplify that? Let's make everything e to the x, or e to the 2x. Multiply the top and the bottom by the exponential function. What do you get? We get e to the 2x minus 1, right, over e to the 2x plus 1. It's not hard to convince yourself, right, that this goes to, essentially, as x goes to infinity, this is essentially e to the 2x over e to the 2x after a while. I mean, plus or minus 1 don't matter when compared to exponential 2x as x goes to infinity. It's huge. So this is tending to 1 as x goes to infinity, right? On the flip side, if x goes to minus infinity, what happens to this formula? It eventually just looks like minus 1 over 1, because the exponentials are tending to 0, right? As x goes to minus infinity, e to the minus twice infinity is very small. So this is tending to minus 1. And so the graph looks something like this. I'm not sure exactly, but something like that. This is the graph of hyperbolic tangent. And that's why the domain of the inverse hyperbolic tangent just involves minus 1 to 1, not included. All right, folks. Well, I'm sure there's something more I have to say about hyperbolic functions, and we'll come back and say it as we need to, as we do more on hyperbolic functions from time to time. I guess one question you guys might ask me is, why do you study? I mean, it's interesting that they're related to cosine and sine, like you showed me, but like, who cares? Like, where do hyperbolic sine and cosine appear in applications, right? That's a question some of you might have. I personally did not learn them in my calculus sequence. I got to a course called special relativity, and then all of a sudden he defined something called the rapidity in terms of hyperbolic tangent, and I was like, what's a hyperbolic tangent function? And we came to the professor, we're like, we never learned this in calculus, and he's like, what? Oh. So yeah, hyperbolic functions are all over the place in special relativity. For example, I mean, it's more than that. It also describes like the natural way a chain hangs under gravity, like the it's called like catenary. The St. Louis arch, always people talk about that. That's like a hyperbolic curve. So hyperbolics are in lots and lots of things. The reason that they're in special relativity is because special relativity is ultimately built over what's called hyperbolic geometry. And hyperbolic sine and hyperbolic cosine play kind of the same role in hyperbolic geometry as sine and cosine do in circular geometry. So they are important. They're in some sense dual to sine and cosine. And understanding hyperbolic sine and hyperbolic cosine will actually help you understand regular sine and cosine more deeply. And that's why I cover them, mostly. Anyway, I hope you don't have a question about this. Yeah, if you have a question about something when I start erasing, you should immediately just interrupt me and go, stop! That's the correct, etiquette. All right. I will now introduce integration by parts. I usually start the course here. I'm starting back a little bit before this because it occurs to me some of you haven't seen hyperbolics or inverse trig stuff in your Calc 1. All right. So integration by parts. What's the idea of integration by parts? Basically, the idea is this. If we differentiate with respect to x a product of two functions, u and v, what that gives us is the product rule, right? We get what? We get du dx times v plus u times dv dx. All right? And that's kind of neat if you look at this then. If we look at u dv dx, that's equal to d dx of u times v minus, well, v times du dx. Agree? And what this means is that I can integrate both sides with respect to x, right? So integrate this with respect to x, integrate this all with respect to x, and what do you get? So basically what's happening here is we're making you might say a v substitution. I mean, you could leave the formula like this, but typically the way people express the formula is as follows, using differential notation. So this is u dv is equal to, what's the integral of the derivative? I mean, I could write this. This is really the integral of d of uv minus the integral of v du. But the integral of the derivative of something is just the something again. So that's uv minus the integral of v du. And this right here, folks, is the famous integration by parts formula. Have you guys ever seen, sidebar, have you ever seen this notation? I wonder if you've ever seen u substitution done in this way. We'll get back to that. Let me show you the standard example. This is the quintessential example of integration by parts. If I want to integrate something like x times e to the x dx, how do I do it? How about u substitution? To quote my community college professor, that dog will not hunt. You can try u substitution all day long. Unless you're very crafty, it ain't going to work. So the standard technique then is to say, okay, so this is going to be what we're going to call dv. This is what I'm going to call u. All right? And so if I trust the integration by parts formula, and I guess I can, I just worked it out. So it's uv minus integral of v du. But of course, what are u? Well, okay, so u, we just said, is x. And dv is e to the x dx. So I usually make a little box over here to organize my thinking. The u and the dv are forced upon us by the original integral. That's not entirely truthful. Once you make a choice of either u or dv, the other three things are forced upon you, right? Once I choose what u is, the rest of it has to be the quote-unquote dv. Anyway, so you guys will have questions once you see an example or two. Let's see here. So du is equal to dx. How do you get to v? What's v equal to? How do we get from dv to v? We integrate, yeah. What's the integral of the exponential? Right. So we're always using this idea of a differential. Do you guys remember differentials from Calc 1? Like df is what? It's f prime of x times dx, right? So that's dv is the differential of v. So, okay. Okay, now that we've done that, what do we got? We've got x e to the x minus what? The integral? E to the x dx, yeah. Which is x e to the x minus e to the x plus a constant. Bam. Yes, sir.
I'm having a hard time seeing like the very first part, how you integrated to get uv minus.
Oh, that's this. That's the integration by parts formula.
Oh, okay, you just took it from there.
Yeah.
That makes sense.
So we can't, there's no, like, wouldn't it be awesome if the integral of f times g was just equal to the integral of f times the integral of g? This is an identity which is often invented by calculus students on tests. Unfortunately, it is wrong. And it tells me I haven't studied and I don't care about your course. That's what doing that says to me. Roughly speaking. No, I mean, this is wrong. I wish it were that way, but it is not. So this is the closest thing we have to that. This is sort of the product rule for integration. It's not, yeah, that's just not the case, unfortunately. Now, the question you're asking, there's actually a question behind the one you're asking, which is, how on earth did I know that's what u was?
Yeah.
Now, that's not very different from the question in u substitution. How do you know what u is? Unfortunately, the answer is kind of the same. Practice. Yeah. Now, there actually is something I can tell you besides practice, and this was told to me by students, and it's usually true. It's the dreaded, well, I don't know if it's dreaded, it's the stupid liate. So this is log, inverse, algebraic, trigonometric, exponential. Now, this is a special rule. It only makes sense to calculus students. If you're a mathematician, this rule doesn't make sense to you because many of these things are the same thing. So this is a troubling, ambiguous rule, the more you know. The less you know, it kind of makes sense. I'm not trying to be insulting. I'm just trying to say it'll make sense to you. So, well, some of you. So you don't know enough to be confused by it. All right, so the point is, basically, whatever you see first here, choose u. So I look at this. I've got x e to the x. There's no logs. There's no inverse functions. That's troubling to me because e to the x is the inverse function of natural log of x. See, that's what I was talking about, the mathematician being annoyed by this. All right, algebraic. Oh, hey, wait, algebraic. X is an algebraic function. Bam, u equals x. See? So if you trust liate, it's so stupid. The natural log of x dx. How do we do this one? By the way, we can't do this with u substitution. You can try all day long. You can't do it. So I go log. Oh, wait a minute. Log. It's got a log. Log is definitely there. So this is going to be u, and by process of elimination, what's left has to be dv. So again, I do uv minus integral of v du. Here we got u equals to natural log of x. So dv is dx. You don't have to make the sound effects. So here du, they'll think you're crazy in the library. dx over x, v is equal to x. If they ever move me back to that cubicle farm we call a math department, I will hold office hours in the library. I'm not going to be part of that. I can't you put professors in cubicles. So annoying. I'm very, very grateful for my office downstairs with walls and a door. I could do without the window. I feel like an animal in a zoo or something. Let's see here. So u times v is what? So I got x ln of x minus the integral of v, which is x, du, is dx over x. Well, isn't that convenient? The integral of dx, which is what? Oh, this brings me to a story. So I was interviewing at a school once, and the guy was driving me around told me about the story of his advisor who used to bring his grandson in after the first test and maybe second test in Calculus 1 or something, where they got the integration. And invariably there would be the integral of dx on the test, and he'd bring his 6-year-old grandson up to the front of the room and he'd say, "Son, what is the integral of dx?" And the kid would go, "Sir, the integral of dx is x plus a constant, sir." And then he would look at them and he would go, "You idiots, even a 6-year-old knows this." Or something like that. I don't know. College has changed a little bit. There used to be a guy who taught Calc 2 at State who was well known. If somebody asked him a question about algebra in the middle of his lecture, he would just turn around and glare at them and go, "Are you serious? That's high school." And then he would just go on. By the time I got there, it was a little bit different. My differential equations professor would say stuff like, "It's just algebra. Relax." And then he'd go on. But I actually do try to respond to your questions in as much as I can. That's it. I will do much more of this when we have time next week. But anyway, go on.
I was going to ask, so for the natural log one that you did, I mean, is there any other possible choice for you? Could you have made dxu?
But then that would beg the question: how do you integrate natural log? See, whatever you make dv, if it's not something you can integrate, it may or may not work for you. I mean, if you can't integrate v, you can't execute the formula uv minus integral of v to u. Now, I have lectured at probably a speed which you will be more happy with in a course called Math 126 on the same topic. I will try to send you guys some links. I have, I think, about at least an hour of just working integration by parts, the simplest integration by parts examples very slowly. Oh, the bad thing about those lectures is I've switched the meaning of v and u mid-lecture, so I'm not sure if I should share them with you. Is that going to be a big deal if I do? Is that going to confuse you? You'll just stop watching them and be confused? Anyway, your homework there is a section on integration by parts in your homework, which is why I needed to talk about that. Anyway, that's it. I will stop and ask if you have questions about homework. So, I'm hopeful in future. What I try to do, guys, my usual mode of operation is to try to lecture the material efficiently and get through it and then have some time for homework questions. But there should be time for homework questions in the week. This week I'm still trying to wrap my mind around. So I'm sorry about the lack of time for homework questions this week. I will try to adjust in the future. So are there questions?
Is it regarding to the homework in general for this week?
I think we should focus on the homework which is due Tuesday or Monday. What is it due? Monday, yeah.
37.7.
Oh, one of the things I didn't do in here, it just occurs to me. It hit me at the end of class last time. I should do something with one of those triangles. I showed one of you this, but some of you will have questions about this, I'm sure. The triangle with the cosines and sines and stuff. So if I had some triangle, say like this, suppose this angle was theta is equal to, I don't know, inverse cosine of x. I'll just do this as an example. Well, I could put an x here and a 1 here. That would be consistent, right? Cosine of theta should be adjacent over hypotenuse, which makes sense, right? That's what? X over 1. So then cosine theta is equal to x, and theta is equal to inverse cosine of x, right? So the triangle, what I'm trying